All right, in our last segment, we looked at the partition function associated with translational motion, right? And we found that we would get quite large values for that. Right at the end, we were calculating a three-dimensional translational partition function, and we had a value somewhere approaching 10 to the 30th power, right? So we have an enormous number of translational states that are populated. In this video, we're going to go ahead and assemble the pieces we need to do the partition functions associated with rotation and vibration, and also with electronic states. So there's a good bit in this one. First of all, remember the overall definition of the partition function. And so this is one form of it here. In this case, my summation is over energy levels because, and I can tell that because I've got the degeneracy term in there, right? The G is the degeneracy. Right? So that means I'm summing in this instance over energy levels I, with degeneracies G sub I and energies epsilon I. We want to do rotations, and so we're going to put in the rigid rotor expressions for both the energy and the degeneracy. And down here, if I look at this piece, the 2J plus 1, that's my degeneracy. And then up here, everything to the left of the KT, that's my energy, right? For state with quantum number equal to J. So that summation, if I can evaluate it, should give me the rotational partition function, which again, remember that's going to be correlated with the number of rotational states that are actually substantially populated. That partition function should go up as we raise the temperature or down as we lower the temperature. So question is, can we evaluate that summation? And the answer is, as a summation, we can't easily do that, but we can take advantage of the fact that for rotational energy states, the spacing between energy levels is generally going to be very small compared to KT. Right? KT at room temperature is what, about 200 wave numbers, and rotational energy level spacings tend to be like a few wave numbers. Okay, so there's a pretty big difference between those two numbers. That means a lot of rotational states should be populated, and that means that our summation can be reasonably approximated by an integral. Okay, so here we've gone ahead and replaced the sum with the integral. We were summing over J, so now we're integrating over dJ, right? My J quantum number can go from 0 and up, and in principle, there's no upper bound to that rotational quantum number. So we integrate from 0 to infinity. This integral turns out to be relatively straightforward to evaluate if you make the substitutions noted here. Right? If I do these two substitutions, then what I get is a standard form that just looks like this, okay? And if I do that, the standard form says I just want 1 over A. This was my A, so if I flip that, I will get what I want for the partition function, which says my rotational partition function can be defined this way. I is the moment of inertia of the molecule. I've got Boltzmann's constant, I've got the temperature, and I've got h bar squared down there in the denominator. Right? So that gives me a reasonably straightforward equation that I could use to find my rotational partition function. We're going to focus for most of this video on diatomic molecules, by the way. So that way our moment of inertia is relatively simple to calculate, and we can do things in just simpler form for that. And that will cover us for most of the molecules we'll consider in detail, at least in the course. So this is the equation we just had up here, right? And because we converted the summation to an integral, and we did make that assumption that lots of states were going to be populated, and what that means is that this expression, we can think about this as a high temperature limit, okay? Because as the temperature goes up, I'm going to populate more and more states, and then KT is obviously going to go up as I raise the temperature. So my approximation that KT is a lot bigger than the rotational spacing will get gradually better as the temperature goes up. Oftentimes, this equation is written in a sort of simplified form using what we might think of as a reduced variable of sorts. So this version down here has in it, the denominator is this rotational theta, also sometimes called a rotational temperature constant. That's defined as it says here. Either h bar squared over 2I times k, or because the rest of that is also what we call b, the rotational constant, we can say it's just b over Boltzmann's constant, all right? That theta parameter is going to have units of temperature, okay? And therefore, when I do this, it needs to have units of temperature because this expression is a partition function, and partition functions don't have units, right? So if the partition function is T over theta, my theta needs to have temperature units. B, remember, has energy units, right? Typically, we talk about B in wave numbers, but we could convert that to joules. And then Boltzmann's constant is in joules per Kelvin. So if I evaluate that, I would in fact get Kelvin by dividing those off, all right? Those rotational thetas, you can find some values for several molecules for that parameter in a table in chapter 5. I don't have handy the page number, but it is somewhere around the discussion of the rotational and vibrational partition functions. So around the sections that you'd be looking at corresponding to this part of the course is where you should find that table. Okay. You can also just, of course, Google for them and find reasonable values for a lot of simple molecules, at least. I'm going to do a little bit of work here to work through what is example 5.f in the textbook. Page number reference is on the slide there. And the reason we're going to do this, it's not, wouldn't normally work through something that's an example in the textbook because that seems almost redundant, but it turns out that in the printed textbook, at least, this example is significantly wrong in the textbook. I'm honestly not sure if that's been corrected in the ebook or not. I know that some publishers, my own publisher for the Chem 107 book, I know will make corrections to the ebook without having us go through a full revision of the printed book, but I don't know if that's the case for this one. So the problem asks to find the rotational partition function for CO, carbon monoxide at 300 Kelvin, and to compare doing that in two ways. One is using the high temperature limit formula that we just worked our way towards. And the other is just sort of a brute force method to just actually calculate the summation of terms for enough terms that we get to the point where the subsequent terms are small enough to neglect. Okay, we'll do the first part, the high temperature limit first, and then I will flip over to an Excel sheet to look at the summation term because I'm not going to calculate a long string of terms manually here for us to look at. So let's do the first piece. I started here with the moment of inertia, right? We could find the moment of inertia if we had to. We would need to get the reduced mass and we would need to know the bond length to get that moment of inertia, right? But the moment of inertia for carbon monoxide is as written there. And so my rotational temperature parameter looks like this. H bar squared, H bar rather, is equal to 1.05 times 10 to the minus 34th power. That's in joule seconds, just like regular old H. If you are stuck and need a value for H bar, if you know Planck's constant, just plain H, you can always just divide that by 2 pi to get H bar, or you can just look it up separately if that's an available option. I have a 2. I have my moment of inertia from up above. And I have the Boltzmann constant. And if I multiply all that out, my notes sitting beside me here say I get 2.78 Kelvin. So that number, the small size of that number, suggests that at room temperature at 300 Kelvin, we should pretty likely be in a high temperature limit, right? Because our temperature is 100 times greater than that theta, and that means that our partition function should end up being decently large, and we'll prove that here in a second, okay? If you look down the table that's in your textbook, you will find that the values for the rotational thetas tend to be between a couple and maybe 10 Kelvin, something on that order for most small molecules, okay? Then I do my Q, which is now we can do the easy form of that, which is just that it's T over theta. Labeling the thetas with rotation here because we're going to introduce a similar parameter for vibration later on in this video. That's 300 Kelvin up here. It's 2.78 Kelvin down there. So it's clearly on the order of 100, right? And divide that out, and my notes say I get about 108. For my rotational partition function. That says I should have 100, 108, somewhere around there, states that are substantially populated at 300 Kelvin, according to that number, right? It's a decent sized number. It does suggest that we're probably safe on our high temperature limit, although if you compare that to the number we had for translation, it's obviously far, far below the 10 to the 20, 10 to the 30th power that we have there. All right. I'm going to flip over and change into Excel, and then we'll pick up there. All right, obviously I've changed the backdrop here, and we're now in an Excel spreadsheet, which I put together to try and do this manual summation of things, okay? Let's, before we look at the graph and the actual result, let's see what's in my spreadsheet. Over here, notice I've got a column that's J. I've got a column next to it that is 2j plus 1, and then I've got a column for j times j plus 1. That's because all of those things figure in the expressions that we have to work with, right? 2j plus 1 is the degeneracy, and then there's a j times j plus 1 term that's in the energy piece, right? So we're going to need those to figure things out. I go down in my j's, I just start from 0, and I go down, I don't know how far I ran this thing, I ran it down to j equals 50, it looks like. Then I've got pieces here for the things that I need. The one that's called term in the Q summation. In that summation to get Q, if I do it by the original, just really evaluating the sum instead of switching to the integral, I get a term for each J state, right? And that term is always, it's the degeneracy, then times e to the minus the energy over kT, right? And so if I look at this, I see that my expression up here, that's going to be a little bit hard to see probably, but I don't know of a way to make the formula bar show in larger type. But it says I've got, for this one, I've got B2, which is my 2j plus 1. So that's the degeneracy. Then I've got e to the minus, I've got C2, which is my j times j plus 1 term, right? And then I've got 2.78 because that's the theta parameter we just calculated, and that's actually got most of the stuff that's in the energy expression. And then it's got H1, which is this one up here, which is labeling my temperature, okay? So that same formula will calculate the appropriate term as we go down the column. And then this one, the last column over here, this one is the value, the term for that j divided by the full sum of all the terms, right? So that's the probability, right? And if I do that, if I scroll down to the bottom, down to here, this one is the summation of all of the terms in my partition function. Notice that I probably went further than I had to, because by the time I get to j equals 50, my next term is 10 to the minus 9th power, right? So I really didn't need to go quite that far out on things. This does sum to about 108, right? I get 108.2, which means I do match my high temperature limit result that I got there. Also notice that the sum of the probabilities is 1, which it needs to be, right? If the sum of the probabilities is not 1, then I've done something wrong, because the molecule has to be in one state or another, okay? If I come up here, this one just links to that cell at the bottom, so I can display the partition function up here with the temperature. So at 300 Kelvin, the temperature the problem referred to, this is what we would get for a plot of the probabilities or the populations versus J, okay? Notice the maximum in here, the most probable J, looks like it's around 7 for 300 Kelvin. Right? And I didn't lock how the axes are set here, so when I change parameters, things are going to happen to the scaling of the graph, and I apologize for that. But suppose I lower the temperature. If I take my temperature from 300 down to 100, that should get my population stuck in lower energy states, right? And fewer of them should be populated. So let's just type in 100 there and see what happens to the Q and also to the probabilities there. So if I do that, first of all, my partition function has shrunk, right? It's down to 36 now, and so I've divided that down. It's actually proportional to the temperature, right? If you look at the way the equation was that said it's the T over theta, right? My maximum in my curve now is showing up around j equals 4, right? So where j equals 7 used to be the most populated, now it's over here someplace, right? Well past the maximum. And if I go back to the previous one, I'll see that when the graph goes over here, I obviously am stretching out. I've got some population out here in the j equals 20 and whatnot states, right? Suppose I went the other direction. Suppose I went to, I'll go to 600 Kelvin, I'll double. If I do that, my probability curve clearly gets broader, right? Now I've got significant populations extending out into j equals 30 quantum number, right? My partition function is now up to 216. If you're not careful, the partition function might seem like it's too big here, right? Because I'm saying I'm out to j equals 30 and out to 216, but remember there's 2j plus 1 states for each one of these j's, right? So even at j equals 10, looks like it's around the maximum in this case, right? But I've got 21 different states that have j equals 10, right? So that one j value can contribute 21 states to my partition function. There's quite a bit we can see in there. You'll have a homework problem in one of the sets, which you may well want to tackle by making a spreadsheet similar to this one in order to do what is otherwise a pretty repetitive calculation. All right, we're going to go back over to the PowerPoints. All right, and we're back. We can quickly remind ourselves that the 108 number that we had in the spreadsheet does indeed match the 108 number that we calculated here. So our high temperature limit and our actual full summation do match and agree nicely. So that's comforting to know that our limit really did work out like we expected it to. Okay. I think I put in here, yeah, I did. I left in here one of the clicker questions that I do in class, and I do this once in a while in the videos just because I think these things are handy to give you a chance to make sure you're sort of latching on to the right ideas. Let's see, and my head window is covering up a little bit of the writing there, it looks like, but this below just says, and the magnitude of KT. So this arrow over here, from here down to there, the length of that arrow corresponds to an energy equal to KT is what that says, okay? I've got whatever my system is, and I confess I just totally made up these energy levels in the diagram, but I've got a zero, I've got an E0 level, 1, 2, and 3. So I've got 4 energy levels. I've got an index labeling states, which starts at 0 and goes up to 15, right? The question that I guess I asked in this version, this particular time in the course last spring, asked my students to compare the state number 5 here with state number 2, and essentially compare the populations of those. Take a moment and think about that. You can pause if you want to. I will say that be careful because we're talking about the individual states now, right? Because I labels one state, it's not labeling the energy levels. So we're not comparing energy level 2 to energy level 1. We're comparing state 5 to state 2. Because state 5 is higher in energy, that means it has to have a lower population than state 2. Right? In the limit that the temperature went to infinity, then all the states would get equal populations. But at any finite temperature, lower states always have higher populations than higher states. That means that the correct answer to my question is that what the value for 5 has to be less than the value for 2 over here. Right? If I had asked to compare the probability for being an energy level 2 versus energy level 1, that one we couldn't easily do. We'd have to somehow account for the degeneracy factor, right? Because I've got a higher degeneracy there than I do here. And that one I couldn't really cleanly answer, I would say. Given that we know KT, we could also say something like, what's a general guess of how big the partition function is? And to answer that question, you need to remember that the partition function tells us something about the number of populated states, right? And if these that are shown here are all the energy states that are lower in energy than this KT value, then my first order guess for the partition function would be that I'd say it's about 16. 16 because I have 16 different states there, right? Numbered from 0 through 15. If we actually calculate it, it's probably a bit smaller than 16 because the population is still somewhat heavily shifted towards the bottom. But overall, that's a pretty good guess of what the partition function would be if we didn't have the wherewithal to actually calculate it. So that's just a little bit of a stop to point out some of the things you can do by just looking at a figure like this. It keeps the focus on the ideas or the concepts behind things instead of on just grinding numbers. And so I'm somewhat fond of questions along those lines for quizzes and exams and things like that, just so that it doesn't turn into a sheer brute force arithmetic course. All right. Let's go on. We have one last point to add for the rotational partition function before we move to vibration, okay? And that is, we started off deliberately, I started off with an example that was carbon monoxide, because that is, gosh, in fancy language, that's a heteronuclear diatomic molecule. In simpler talk, that means the two ends are different atoms from each other, right? And so if I take my CO molecule, if this is it, if this is the carbon and that's the oxygen, right? If I rotate it 180 degrees, now the carbon is over here and the oxygen is over there, right? And you can tell those two arrangements apart, right? Because you can tell carbon from oxygen if you can actually see which one is which, or if you knew the masses of them, say, or whatever, right? So those are distinguishable arrangements. So our partition function calculation was fine for that case. If instead of being CO, if my molecule was O2, then this arrangement and this arrangement would be identical, right? There'd be no distinguishing differences between them. Because of that, we would end up needing to divide our partition function by 2. And so the way to do that is to introduce a factor down here, this thing labeled sigma, in either form of the expression. In the case of a homonuclear diatomic molecule, that would be 2. If I went to a more complicated molecule, if I went to, say, I don't know, a trigonal planar molecule like this, and I was going to rotate about the central point, if all 3 of my outside atoms were the same, then my symmetry number for that rotation would end up being 3, right? Because I'm going to have then 3 different orientations that I can't tell apart, right? So there'll be a symmetry number like that for anything that is not a heteronuclear diatomic in general. Okay, there'll be at least a chance of there being one. In the case of my, this one, if these were 3 different atoms, if this was like A and B and C around the outside, then all the positions would still be distinguishable, and my symmetry number would drop back down to being 1, right? That would be the equivalent of being the heteronuclear diatomic in that case, all right? So for our purposes, the main thing is that if we have a homonuclear diatomic, we're going to be using a 2 here because we're mostly working with diatomic molecules. All right, let's move on from rotation and take up vibrational motion at this point, because that's next on our walk through the different degrees of freedom in terms of their energy level spacing. Okay, our overall definition of the partition function, I'm still writing like this. Here, I've just gone ahead and declared that my degeneracies are all equal to 1. That's because for vibrational states, there are no degenerate states, right? The harmonic oscillator model is what we'll use, and each energy state in there is at its unique energy, right? And so what I'm going to do is I'm going to take that summation, and I'm going to use n for the vibrational quantum number now, because I don't want to have a v and a nu in the same equation, right? And if I do that, my expression will look like this, okay? So it's got, this is the energy, okay? And then I'm summing over the quantum number, which can go from 0 to infinity. All right. Now, notice that we've kind of cheated on the energy expression, right? The real energy expression would have an n plus 1/2 here instead of an n, right? But when we calculate these partition functions, at least for now, we're locking the ground state at 0 energy, right? And so the lowest vibrational state will also get an energy of 0. Then the spacing is h nu, so I'm just going to go with nh nu for my energy, because that's the actual energy spacing is what I really need there, okay? So that's the summation that I would need to try to evaluate for this. If I look at that, it turns out that this is a summation that converges, which is good, because my spacing between vibrational energy levels is generally bigger than kT. Right? So I don't want to replace this one with an integral. Okay, if I just make this substitution, say that x is equal to h nu over kt, then my summation looks like this, right? It turns out that that summation, I kind of left a line out of the slide there, or the equation in the slide, it looks like. But if I wanted to do that in terms of just e to the minus nx, then I would get that that's equal to 1 over 1 minus e to the minus x is what that says, right? Because this thing up here, that is just my x. Right? So if I take that form and apply it to what I've got here, I get this result, okay? That works because this sum here converges, and my summation looks like this because my energy levels are equally spaced, right? And so every term will look like this. In the first case, my exponent is 0, so we just replace that with 1, and it goes on from there. So because of that, we can legitimately evaluate this summation, right? We can't turn it into an integral, but we also don't need to turn it into an integral because the summation itself can just be converted into a closed form. So that gives me an expression that I can use for the vibrational partition function. I can take this one, or I can take this form in which I've again introduced one of these theta parameters, okay? This one is now theta vibe for vibration. That's equal to h nu over Boltzmann's constant. H nu is in energy units, and so that still works. That's got temperature units. I put it up here, and I get a unitless exponent and a unitless partition function, okay? You could find values for those theta parameters, again, in a table in the latter part of chapter 5. If you do look at that table, you will notice that while the rotational numbers tend to be often in like a few to 10 Kelvin, these vibrational thetas are going to be several hundred to 1,000 or 2,000 Kelvin. Okay, so they're much larger numbers because that energy level spacing is much bigger for vibrations. All right. This expression that we've got here, this is an exact equation. It's not a high temperature limit because we didn't make any approximations, right? We just legitimately evaluated the summation, okay? If we had a molecule more complicated than a diatomic, we would have an individual term for each of the vibrational modes, right? For a 2-atom molecule, there's only one vibration, which is the stretching and compressing of the bond, right? If I have more complicated molecules, more than 2 atoms, then I'm going to get multiple vibrational modes. We talked about that in terms of IR spectra. In that case, I could multiply together the various terms to get a total value of vibrational partition function. That's also why, if you look in that table, there are some molecules beyond 2 atoms that are in the table in your textbook. So you'll see some molecules for which there are multiple entries for those vibrational theta parameters. That just means there's a different one for each vibrational mode. All right, so armed with this, it's good to touch base with something that's actually a measurable quantity once in a while. What I've done here is we're just going to take a moment and think about the heat capacity of nitrogen, okay? The nitrogen molecule has a rotational theta of 2.88 Kelvin, which is not surprisingly quite close to what we had for CO, right? We had 2.78 there. The moment of inertia for CO and N2 should be pretty close to the same, right? The bond length's a little smaller for nitrogen, I guess, maybe. The overall, the masses of the atoms are about the same, so that makes sense that it would be similar. At 293 Kelvin, I get a constant volume heat capacity equal to this number here, 20.816 in joules, okay? Question asks us somewhat nebulously, how is that heat capacity broken down across the different degrees of freedom? Well, so far we've talked about translation and rotation. I don't know why I stopped over there, but I'll go back. And vibration. So we'll put those on our list. Okay. The translational motion, that partition function, when we calculated an example of it, it was enormously large, right? So essentially, we're always in a high temperature limit for translation. Because we have 3 directions the molecule can move in, we said before that our translational contribution to the heat capacity, that should be equal to 3/2 R, right? The rotational motion, if the theta parameter is about 2.9 Kelvin and the temperature is about 290 Kelvin, that means my rotational partition function is on the order of 100. That means my rotational motion should be in the high temperature limit as well, just like we saw for the CO case, right? That means that for my rotational motion, I have two rotational modes because I can rotate about two axes, right? Either this one going that way or the one that is going perpendicular to that. So that means I get 2 times 1/2 R, or I get R. Put those together and I get 5/2 R. Right? 5/2 R, according to my notes over here, is equal to, well, it's obviously 2.5 times 8.3. And if I do that, my notes say I get 20.786 joules per Kelvin per mole. If I compare this number up here and that number down there, they're quite similar, right? That says that my vibration contributes just, what, 0.03, I guess, joules per Kelvin per mole. Because that's the difference between those two numbers, right? 81 minus 78 should give me that, that 3. That says that my vibrational partition function, this says my Q vibe has to be very close to 1. Right? Nearly all of my molecules are in the lowest vibrational state. That should make sense. Nitrogen has a triple bond after all, right? The bond is quite strong. So it's going to take a lot of energy to stretch that bond. Vibrational frequency is going to be quite high. My vibrational theta, if I look that up, is going to be much larger than my 293 Kelvin temperature, right? So my vibration is hardly at all contributing to the heat capacity at this temperature. Now, if I raise the temperature, if I made the temperature 1,000 Kelvin, my heat capacity would be going up, and the increase would be due to the growing importance of vibrational motion. But right now, all the molecules are pretty much trapped in the lowest vibrational state. They're not able to climb up to that first excited state, and that means that the vibrational states are not a reservoir into which we can dump energy until the system is hotter, until there's more energy available. Okay, so that just gives us a kind of reminder about how those different degrees of freedom will grow in as the temperature rises or freeze out as the temperature falls. All right, last stop in our tour of pieces of the partition function is the electronic partition function. Right, our overall definition still looks the same. Right, it's this way summed over energy levels. For my electronic states, I could write out a series of terms like this, right? Where this piece, my ground electronic state, I'm again going to be calling 0 energy, right? And so it should be true that this piece will just be the degeneracy. And then I'll have subsequent terms here where the magnitude of those terms depends on the difference in energy that's up in this exponent, okay? My subscripting's a little off in there. I didn't get out of subscript at some point, it looks like, but oh well. So if I take that, the next thing to think about is the fact that the spacing between electronic energy states is generally very large, right? We know that because we know that electronic spectra happen in the UV or the visible region of the spectrum. Those are high energy photons, relatively speaking, right? And so we expect those energy spacings to be wide. They should be much bigger than KT. Because of that, my molecules should be extremely unlikely to climb up out of the ground electronic state, right? Just like you expect an atom to be in its quote, normal electron configuration, the same is reasonably true for a molecule, right? Therefore, we can just about always say that the electronic partition function should be given entirely by the degeneracy of the ground state. Right? If the ground state, for example, has a single unpaired electron, then the degeneracy will usually be 2 because that electron could be spin up or spin down. Right? In other cases, the degeneracy might be 1. Right? And there are cases where it could be different from 1 and 2, but that will cover a lot of them. There are a small number of molecules, and a couple of them are written on the screen there, that happen to have low-lying excited electronic states where we might actually have to evaluate a second term in that partition function to get a sensible result. But that's a very uncommon situation. So in general, we will use the presumption that the electronic partition function is just the ground state degeneracy, right? Careful with this equation, because the Q equals G see thing, particularly if you're looking at handwritten notes, that can get to look like it says that something equals itself, right? And so do watch out for that, and make sure that you're on top of that being two different things for sure. All right, now we have all the pieces, and once we have all the pieces, we can build our total molecular partition function. All right, so this is it. All we have to do is multiply all the individual terms. Right? When we do that, because our molecule is going to simultaneously be in a translational state and a rotational state, a vibrational state and an electronic state. So its probability, for example, is going to be the product of the probabilities for the individual components, right? And if I take that and insert the results we've put together, I get the equation on the bottom, where this piece is the translation. This piece with the theta rot in it is the rotation. This one is the vibration. And this last one is the electronic term, okay? If I take that full product, and if you think about the magnitudes we've seen, it should be clear that the translational term is going to dominate, right? Because that in general is going to have an order of magnitude that's like 10 to the 20th, 10 to the 30th. My rotational, the couple we've looked at in the video today, have been on the order of 100, right? So decently large, but certainly not 10 to the 20th power. Right? Vibrational one is often near 1, and the electronic one is usually a small whole number, right? And so that tells me that the numbers themselves for the partition function will be large, primarily because there are so many translational states. All right, there's actually a good bit in this video, so make sure you digest that. In the next segment, what we will do is we will grab our partition function that we've now assembled, and we will once again return to think about how to link that partition function to some thermodynamic quantities, right? Develop some relationships that will show how we can use that to calculate things that might be of interest in any of a number of chemical situations, things like delta G's, delta H's, quantities like that. And again, the utility of statistical mechanics is that it gives us a route to be able to calculate those sorts of things without having to do calorimetry, right? So the data we use when we do statistical mechanics in general is just going to be spectroscopic information, details that tell us what are the energies of the different states. Once we have those, we can now make our partition function, and next we'll pick up more tools for going from that partition function to the thermodynamic quantities. Thanks.